you see, if you have a non-degenerate perturbation theory, this is the first order perturbation. If K not necessarily equals N, but the energy are the same. In other words, K not equals N, but energy is the same. Then there's a problem. So the denominator diverges. And this, could you guys write this down? In other words, why we need non-degenerate perturbation theory is because when, even though the index K and M are different, but what happens if the energy themselves is the same? And this happens with the P states that I showed you here. You see, P states, if you call this the 1, 2, 3, 1, 2, 3, I'm going to use 1 and 2. And this index 1, this will be 2. But the energy are exactly the same. Then there's a problem. So the wave function diverges. Doesn't make any sense why wave function has two diverges. So this means this one will break down. So the main reason is that the keyword is divergent. The reason is precisely if you have MK not the same, but energy the same, so then you have problems. Make sense? Makes everybody give you a thumb up, understand this part. So that's most important. So I have a second question for Alex. What are the key differences between perturbation, degenerate perturbation and non-degenerate perturbation theory? What's the key difference? Non-degenerate perturbation theory, in which way differs by from the degenerate perturbation theory?
Based on what you just said, I would think the degenerate perturbation theory is an asymptotic series. I would think, but
Okay. I'm going to write this down on board. How about that? I'm going to write it on this board. I'm going to use this board over here. So just make sure there are series of things are same and different, because this way allowed us to see what the key difference here. So I'm going to write this over here. Could you guys write this down? This is so important, because if you learn perturbation theory, what the key similarity or difference which matters to us. So how do we understand the entire working principle? So, and I will first write down the similarities, and then I will show you what the key difference here is. So these are two things which is quite important. So I'm going to show you now. So here is the non-degenerate perturbation theory. So I use NDPT. And this one is a degenerate perturbation theory. So I want to show you the similarities or difference. The first similarity, so I'm going to write down this column here. Something similar. Similar. So they will be similar to each other on the first line here. So let me put over here. So that's the similar. They will be. They only target one state. Should be one eigenstate. They are the same. In other words, there's no need of separation. They only target a single state. They do not target all of those states that you have. Second, so this is the first state that you have. Second, they make assumptions. The H0 naught equals epsilon K naught is known. So they're assuming that all these eigenvalues for the non-perturbative ones is known. So this is a known assumption. Number three, the perturbation part is smaller, sometimes much, much smaller than H not 0. So they're much, much smaller. So again, there are three things are exactly the same. And the target, the one eigenstate, and this is assuming no, and this is smaller than H naught. So that's the similarities. Now what's the key difference? Key difference is the following. Let's in terms of the first order wave function. So here we need a separate now. So they are the same, but the bottom one is different. For the wave function for the first order, we have summation, and we have the coefficient in the front like this, and I use letter I to representing that. So that's the K like this. And the first order corrections, it is written over here. So it's written over there. So in other words, that's first order corrections, like these brackets. Please use the one that on the right hand side, and then you have EK. Here let's use M and EM like this. So all these metric elements is written over there. I'm not going to repeat. So that's the first order. But the general perturbation theory, this one is actually psi K. Summation C has got an I. Let's see M, that's fine. CM phi M. And this M runs from 1 all the way to number of degeneracies states. Let me rewrite this equation a little better. I just want to be extremely precise. This will be C, let's use mu, 1, and M to the mu, and this will be mu, phi, and here you will have 2 index, mu, they're like this. So, and first order perturbation is C sub mu, C sub M, forgive me, C sub M, sorry. C sub M, and so this M runs over M, runs over all the degenerated states. Here M runs over all the states. So there is a big difference. For the degenerate perturbation theory, this M runs from all the degenerate states, belongs to K, was connected with a K, like this. So that's just like P orbital, then you're going to have Px, Py, Pz. So this run Px, Y, Pz, and that is the key difference. Did you see the difference here? One is run over all these states. Well, possibly you have a fixed number of states, but that's the all states we will use in order to do the calculation. The eigenenergy is similar, so this will be not similar, actually quite different. Eigenenergy, the first order, is just expectation value of K. So this first order. Second order is much more complicated. I'm not going to write this here. And here, the energy EK is the eigenvalue of the matrix H hat, like this. So that's the matrix H hat. So this is the eigenstate of H matrix. That matrix hat. This is what we are using. Let me move my laptop slightly away so that way we can see over here a little better. Yeah, so this is the one that I want to explain it. And these are the key difference between degenerate and non-degenerate perturbation theory. Are we good so far? Okay, so you got to write this down. This is quite important. Let me move on. Okay, all right, that's the only comment on the exams. So some of the questions that are on the exam that I noticed was the similar to the homework problem, but not handling correctly. But if you guys want to talk to me about the exam, please do so. So I'll be more than happy to address them. And my plan is that I want you to reinforce this idea. Do you guys want to have a bonus on the exam too? Yes or not? Give me a thumb up if you like it. Okay, good. So I will have similar bonus points on the exam for the next week's quiz like this. Sounds good? Okay, make sure you do catch that. All right, I don't need so many more, so I'm going to close this now. Stop sharing. Okay. If you guys have any questions, please do talk to me, and that we will be able to resolve it. And so I am going to use this board. And I need this. Let me put it away back here. So today we will continue on what we left over last time, and this allows us to explain what the key idea for us. So this will be, let me lower the camera slightly. Okay, a little too high. That should be good. All right, so now we are going to continue on the examples we started last time. Let me grab my notes. So last time we read a little bit, which is very, very good for us. And now what we will do, we will show you some additional examples, and then how do we do the calculation with the non-degenerate, degenerate perturbation theory. So that's some examples which we will use today. So I think we finished reading all of them. So that's a second order perturbation. Okay, so we did finish the reading, and then the non-perturbation. So last time did we finish the reading 5.3.2? Could you guys check the textbook? Did we finish that one? Yeah, let's look at the textbook. Let's check, see where I think we did the zeros order correction. Did we just zeros order correction? Okay, so zeros order correction is we done. What else we read?
Yeah, we stopped right before there. Yeah.
It's the first order correction we did not go over, right? We just stopped zeros order. Is that right? Okay, so let's go there, and so this is the zeros order. Yeah, let's plug it in. So this is what we got here, diagonalization section. Yeah, this is diagonalize it. Page 5.3.2. Yeah, exactly. So that's a zero. That's essentially a zeros order. So essentially what we did was we just matched this up. And now what we will work, this will be step number 4. And this part is going to be the first order. Zeros order is clear, and this will be first order. So this will be first order the correction. So this first order correction. So the first order correction, essentially we use the same thing, except that the first order correction will be how the lambda 1 is going to be utilized. So folks, we're going to read from section 5.3.3. Cody, could you read first order corrections 5.3.3? Yeah.
Zeroth order or first order?
First order. Zeroth order. Did we go over the zeroth order? We haven't. Let's go to zeroth order then. Yeah, go ahead. Go zeroth order, please.
For theta zeroth order, we have
no, lambda.
Sorry, lambda zeroth order. Sigma from I equals 1 to eta h hat sub 0 c sub I to the zeroth order of phi sub I equals e sub k to the zeroth order, sigma from j equals 1, and eta c sub j to the zeroth order, phi sub j. We multiply direct notation phi sub k from the left and integrate it to obtain sigma I equals 1 of eta c sub j to the zeroth order direct rotation phi sub k h hat sub 0 phi sub j equals e sub k to the zeroth order sigma j equals 1 to eta c sub j to the zeroth order direct notation phi sub k phi sub j. Since phi sub j is an eigenstate of h hat sub 0 h hat sub 0 and phi sub j equals epsilon sub I phi sub I, we can rewrite the previous equation as sigma I equals 1 eta c sub I to the 0th order epsilon I phi sub direct notation phi sub I, sorry, phi sub k phi sub j phi sub I t sub j equals e sub k to 0th order sigma j equals 1 eta c sub j to 0th order. I'm losing my voice. Direct notation phi sub k phi sub j equals epsilon k, which equals, or goes to epsilon k, which equals phi e sub k to 0th order, where we have used the orthogonality direct notation phi sub k phi sub I equals delta I k. This proves that the 0th order of energy E sub k to 0th order is just epsilon k times c sub k to the 0th order. Can choose any values. So the 0th order wave function is the same as an unperturbable function.
All right, thank you so much. It's quite difficult to read. All right. Okay, anyway, so for the 0th order correction, folks, could you guys write this down? So the 0th order correction for the eigenvalue is just the initial non-perturbate the results, this 0th order. And this k can be chosen any values. Now this k, we write a little lousily, should have another index, let's call it m like this, should have another index m. But it's because there's so many indices. This m runs from 1 all the way to mu. So this is how many degeneracies. When we first write this, we thought we just add an index, but it turns out too many indices, you get bored. So essentially, this guy is equal to that. So that's, for instance, if for the p states, this will be px, py, pz. So that's the wave function. Now the wave function, the 0th order, you can choose any arbitrary linear combination of the ground state. So here's a k. Again, this k can be km. You can choose any combination you wanted. They will be exact same. In other words, you just simply choose this one be fine, or choose this one be fine. 0th order m. You choose this one will be fine. It doesn't matter which one is, because these are all degenerate. So you can choose any state. So this m can be arbitrary in the sense that you could, as far as you normalize it, so this will be fine. So you can choose this, so there's no difference. That's for the 0th order in this case. Or like this. Okay, so that's the 0th order. So now, once we understand 0th order, we do the exact same for the first order. So 0th order will be lambda 0. First order we will lambda 1 like this. So we will use the coefficient lambda 1 to do the calculation. So then match both sides with everything with a lambda 1. So this is the second part of our discussion on the degenerate perturbation theory. Alex, could you read until from first order correction all the way to equation 5.3.8, like that?
Now we can say the first order correction, lambda 1 term, lambda 1, the summation y equals 1 to mu, open quantity, h naught hat, c sub I 1, phi 1, phi I plus h sub I hat, c sub I 0, phi sub I equals quantity equals summation from j equals 1 to mu, open quantity e sub k 0, c sub j 1, phi sub j plus e sub k 1, c sub j 0, phi sub j closed quantity.
Okay, hold on 1 second. Folks, did you see the subscript here we use j? Did you see here? The left-hand side we do is I. Did you see here? But they all run the same way from 1 all the way to mu, like this, run the exact same way. The main reason we write this, did you see left-hand side we use summation over I? The right-hand side summation over j was that when we have this book, some books they use exact same index, and the student will think, well, both sides equal to each other. No. In principle, the summation, but it does not mean they will be equal to each other. That makes sense to all of you? In other words, summation over I, summation over j could be completely independent from each other. So that's what we purposely in this book use different indexes. Okay, go ahead, please.
We multiply bra phi sub k from the left and iterate the resultant equation to form summation from I equals 1 to mu, open quantity c sub I 1, bra phi sub k, h naught hat, ket phi sub I plus c sub I 0, bra phi sub k, h sub I hat, ket phi sub I closed quantity equals the summation from j equals 1 to mu, open quantity e sub k 0, c sub j 1, bra phi sub k, ket phi sub j plus e sub k 1, c sub j 0, bra phi sub k, ket phi sub j, closed quantity. Since bra phi sub k, ket phi sub j equals delta kj and bra phi sub k, ket phi sub I equals delta ki, the result of the equation can be further reduced to e sub k 0, c sub k 1 plus the sum from I equals 1 to mu, c sub I 0, bra phi sub k, h sub l hat, ket phi sub I equals e sub k 0, c sub k 1 plus e sub k 1, c sub k 0. Canceling the first term on both sides and rewriting.
Oh, hold on, you basically, thank you so much. Okay, any questions from equation number 5.36 to 5.37? Any questions? That's basically left side, just brackets, phi sub k, and that's what we do. And then the next two lines just gave you orthogonality, and that's a relationship. That's all you need. Okay, Aisha, could you move on to the next sentence, please? Canceling.
Canceling the first term on both sides and rewriting e sub k to the first order, c sub k to the zeroth order as e sub k to the first order, summation of I, c sub I to the zeroth order, delta ik. We have the following secular equation. Summation from I equals 1 to mu, bra phi sub k, h sub I hat, ket phi sub I minus e sub k to the first order delta ki times c sub I to the zeroth order equals 0, where c sub I to the zeroth order is no longer arbitrary in contrast to the zeroth order.
Thank you so much. Let's stop here. So the above equation, that is look like very, very nice equation, which I'm going to write this down. Could you guys write this down? And this is the place that I need to explain it, what this is actually about. This is the 5k hi hat phi I minus ek 10 sigma ki, and that's it, and have c I 0 equals 0. When I was a student and learned this part, if the professor written like this and eventually gave you a matrix, it's always totally get confused. How in the world do you get the matrix out from this? This is just summation, all of those ones. How do you can expand as a matrix? So I'm going to explain why this is a matrix. Did you see my K here? This K is not arbitrary. No, this K is not arbitrary. K runs from 1 all the way to 5. Just remember, when we say targeted one state, we only targeted a single state here. Did you see it? We only targeted one eigenstate. In the degenerate perturbation theory, you are targeting eta number of states. Could you guys write this down? When we say 1, for the non-perturbation theory, the degenerate perturbation theory is a group of eta. A group of eta. Could you guys write eta states should be? The reason was it's difficult to explain it immediately was that the non-degenerate perturbation theory, I will target k equals 3. But degenerate ones, k equals 3, well, you have a multiple of states. So therefore, you will see a group of the eta state, of new state. So that's why here it runs from 1 to 8. Does it make sense to all of you? Could you give thumb up on this part? Yeah. Make sure you understand. This K is really runs from 1 to 8. Even though we say target one state, but one degenerate state, that's the problem. So that's the degeneracy is kills us. All right. Now for the I, and this I runs from 1 to mu also. So they both run both ways. And then you could imagine this is going to be a matrix. And I'm not going to use these kind of numbers to show you. I want to be confident. Let's say the mu equals 2. How about that? So then you will notice that my mu equals 2, this entire line here, this line here, is going to have a matrix elements look like this. When the I equals 1, I would have when I equals 1, k equals 1, I have this matrix elements. 1 here. Let's forget about this for the moment. That's not the most important. The most important part is it. That's first element. Second element will be phi 1. I stick with k equals 1. So this is going to be phi 2. So in other words, when the k equals 1, that's the two elements you're going to have. So this is the way. Could you guys write that when k equals 1, I will have this. Does it make sense to all of you? In other words, if I stuck with a k equals 1, I will have these two elements. Now, on the other hand, if a k equals 2, then the first one will be phi 2 h 1 hat phi 1. Second element with phi 2 h hat phi 2, like this. Did you see it? Did you see it? So now you can notice that here is the matrix elements of 1, 1, 1, 2, 2, 1, 2, 2. Did you see that? Did you see that? So this is a matrix. In other words, if I write this guys down, this would be 2 by 2 matrix. So I'm going to make things a little simpler because this is much harder to write. I'm going to write a matrix elements directly without hat, and this is the matrix elements now. So now I do not have hat anymore because this is the matrix elements. So I have a 1, 1. And here's 1, 2. Matrix elements, remember there's no hat. And here's 2, 1. Here's 2, 2, no hat because this is matrix elements. So that's why no hat here. You see? No hat, no hat, no hat, no hat. These are matrix elements themselves. Now, did you guys see this is a 2 by 2 matrix? In other words, if I have degeneracy is equals 2, then I would have 2 by 2 matrix. So this is the one from here all the way to that. It's a 2 by 2 matrix. If I have eta equals 10, then we're 10 by 10 matrix. So this is the matrix element. Now, we have second term. This is the diagonal term. Essentially, it would be minus ek1, and here's ek1 here. And I can move this diagonal to the right-hand side, and you will see immediately. So this is essentially what the matrix elements. And then you have this one here. There was C10, C20. So like this. And this whole thing equals 0. So this line here is a matrix here. That's eigenvalue problem. Did you guys see it? Did you guys see? Can I get thumb up? Everybody give me thumb up. So this is the eigenvalue problem. Essentially eigenvalue problem. In other words, to be more standard eigenvalue problem, I will move this guy to the right-hand side and give you the eigenvalue here. So that is what we have. So, and this is just eigenvalue problem. We will show you a little more detailed. And then, in order to solve for this, then all you need to just take this guy as a determinant and solve the determinants. Let's say determinant equals 0, and then you have non-trivial roots for this matrix element. And when you solve it, our job is done, because when you diagonalize this matrix, these two will be known, and this will be known. So then when these are known, then we'll go back to what we did before. So that's expansion. So that's once that element is known, so this guy will be known, and this will be known. Did you guys see the logic here? So that's a step. Okay, I'm going to highlight this for you guys. In other words, so here is the first things, and here's the second things, and then finally we plug into. So that's the logic from 1, 2, and all the way to 3. So then we solve all these eigen states, and that's the final results, which we got over here. And the remaining portion of the textbook is just doing exactly this thing. It solve for this and it get a series of these eigenstates. So this is the end of the results. So we have about 10 minutes remaining, which is almost awesome place. So we're going to use this theory to solve one of the most exciting examples for the H2 plus molecule. This is the hydrogen, the molecule now. It's not regular atom anymore. So that's why I like this part of the physics side of it, because it just shows us which we can now solve our problem for our real example, which is we are going to discuss now. Okay, so this is a true example. This will be my section, the year 4. So this is the application, section 4. I jump a little bit. I thought of nearly degenerate. Let's do section 3. It'll be fine. That's no problem. It's called section 3. And here's example starts. So we're going to show you some examples. So this is the example which I purposely designed this particular example is because I found out this was really crucially important, and it gave us a whole lot more information than as we needed. So I'm going to show you an example now. So this example, we will show 2 examples, and both of these are really interesting examples with the degenerate perturbation theory, how we actually do the calculation. So our first example is H2 plus molecule. Now you may wonder, last chapter we only talked about the hydrogen atom. Most of these books postponed this perturbation theory for long, but now we see we can deal with the H2 plus molecule. And I'm going to show you what this H2 plus molecule look like. Here's my hydrogen atom when this is nothing to do with the Hamiltonian, it's a hydrogen atom, so this edge is situated here. And I have another hydrogen atom situated over here. And they have a distance between them that's called r. So that's distance. Now, you may wonder, Dr. John, why do you just use a plus, not just a regular neutral? No. If I have without plus, we have 2 electrons. The problem becomes much harder to solve. And here is simpler in the sense we just have a single electron. Folks, let's put electrons over here. So that's net B, like this. This electron situated like that. And Alex, what happens if I do not have any electrons on this molecule? What will happen?
There's no bond.
Yeah, they're going to completely separate. It's just stripped away all of. So the electron will only glue, so to speak, and then they form the bonds. Good job, excellent, wonderful. So now what we want, first distance from this hydrogen atom to the electron, that's our radius r. From this hydrogen atom, we use the radius r prime. So this is the one of the r and the one of the r prime. And that's what we use. So we will use step-by-step fashion, exact same as we did last time. First, which we call step 0. Step 0 is basically the original Hamiltonian. So any physical problem, you have to know what the Hamiltonian looks like. So that's why it's important. So here's a Hamiltonian. This edge is the Hamiltonian, just equals the kinetic energy term, that's T, and plus potential energy from the hydrogen number A, and plus another potential energy from hydrogen number B. Did you guys see that I only have one term for the kinetic energy? The main reason is because I have one electron. Could you guys write this down? Because I have one electron only. Had I have 2 electrons, watch carefully. If I have 2 electrons, this Hamiltonian would look like this. T1, electron number 1, T2, electron number 2. So that's what you need. And then V will have a whole lot more terms. So the V will have a whole lot more terms. The first term will be the electron number 1 and the hydrogen A. Second, VA, electron number 2, hydrogen A. And the second term will be VB, electron number 1, hydrogen number B. And the third term, fifth term, and the sixth term now, the electron number 2, hydrogen number B. Did you see if I had one more electron, I would have, how many terms I would get? Whole lot more terms comes out. Did you see that? That's the problem. This is not the end of it. We also have electron interaction terms. Did you see? When we choose examples, if you have like this, it's you can overlook this. So how many terms extra? You add one more electron, so that's why quantum has become so hard to do. If you add one more electron, gee, I add a whole lot more terms. If I have 3 electrons, you will be 3 electrons. A quantum mechanics, quantum chemists, just like the landing, they're doing the maximum number of electrons they can handle is 14 electrons. 14 electrons, it's so few electrons. That's why we literally use density function theory, which use that. So that is the main reason. Now, in this case, what you want to see is the following. So this is the single electron, and that's the potential. This is another potential due to this part. That's the first Hamiltonian which we have. Second part, which we will use, is the following. This time, our interest, so this is the second, and this is step number 1. We're going to choose the degenerate state, 1s states. So these two 1s states is when they are isolated. They are isolated. When these two H atoms are isolated. So this then means the H hydrogen atoms are isolated. These are the wave function which we want started with. So these two wave functions. Now I'm going to write down these two wave functions. This is a degenerate states because when they are infinitely separated, these two states will be exactly the same energy. So I'm going to show you the first eigenstate. Could you guys write this down? This is phi sub A. That means first eigenstate. And then we are talking about a 1s electron, so we just put the 1s there. The wave function is as follows: square root pi A0 cubed, that's square root, and e to the negative r over A0. So that is the wave function for the HA here. Another wave function, which we've got phi sub B, 1s state. Same thing here, there's no difference. But now watch carefully. This part has A prime, R prime. But because this is with respect to the HB, that's why this distance would be the R prime. Okay, so this is the one which we have. Step number 2. We're going to separate Hamiltonian into H naught plus H hat. And that separation is exactly the same as we did in non-degenerate perturbation theory. Exact same, there's no difference. So in this case, just save my time, folks. We're going to denote this part as my H0. Denote this part as my H0. My H sub I or VB. Okay. Or VB, like this. So this is, so in other words, you're going to see me, we're going to use this part, this part, this part, to form a metric element like this. And you're going to see me to write a 2 by 2 matrix. So on Friday, what we will show you is that this, the metric elements, this metric elements is going to formed by AA, AB, BA, BB, like this. So the 2 by 2 matrix, you will be seated. Okay, you know that's what we do. So these are the eigenstates when they are isolated, and we'll come back to this on Friday. So class ends now. Homework due on Friday. Make sure you finish on time. If you have a question, make sure you talk to me. All right, sounds good. Any questions before I close it? So far so good. All right. See you guys on Friday.